to be talking about some of his research, and I was hoping that we could, observe Mercury as a sunspot on Monday. You never know. You can probably still observe it online as one. But instead we're going to hear about Starspots. So thanks, Don.
You have to forgive me, I'm going to be referring a little bit to my notes because I changed the talk around a little bit kind of last minute. As I originally made a shorter talk in anticipation of it probably being clear tonight, and folks wouldn't want to be sitting here and someone blah 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 a whole long time. But it's cloudy, so I'll take advantage of that, and I added some stuff in. So please forgive me if I'm periodically staring down here at my notes. So again, for most of human history, the sun and stars have been worshipped. They have been sources of inspiration, wonder, romance, and fantasy. Only in the last century have they begun to surrender their secrets. The difficulty was that astronomers could only resolve the surface of one star, the sun. Other stars were much too far away to be seen as anything other than points of light. This limited our understanding about the nature of the sun and stars. Indeed, for a long time, many astronomers assumed the sun was unique among the stars. As technology advanced, as well as innovative techniques to study the light from stars, more, of course, was discovered. I'm going to focus on one particular phenomenon that manifests on some stars, spots. I'll also discuss the project, as mentioned, I'll be working on in collaboration with Ohio Wesleyan's Dr. Robert Harmon and Dr. Gregory Henry, Texas State University, related to this topic. And I'll ask you, if you can, hold questions and comments till the end so I can get through this, right? So, to begin with, we'll take a little historical journey. And forgive me, I'm going to ask some questions of you through this talk. Let's start with, when were sunspots discovered? When do you think sunspots were discovered? Anybody know?
Chinese. Imperial Chinese.
Right.
So
okay, so.
10th century.
Right. Well, they've probably actually been observed for a long time, even before written records were recorded. The earliest records, yes, were the Chinese. They would chronicle observations of sunspots in this book called the Book of Changes, related to changes in the heavens. This dates from around the 8th century BCE. And basically what they would do, large sunspots, usually in the order of an arc minute or so, are actually visible to the naked eye. They would observe them at sunsets or on very hazy days or a little bit of high clouds, high thin clouds. So this, of course, was stupid. Of course, you should never look at the sun. Don't look at the sun ever, okay? The first clear observations in Western literature occurred in the 3rd century BCE and noted by a Greek scholar, I can never pronounce his name right, Theophrastus? I'm not Greek, student of Plato and Aristotle. And the earliest known deliberate observations were made by a Chinese astronomer named Gandhi in the 3rd century. And by deliberate, I mean he actually set out to observe these things and actually try to see them. And it wasn't until the 1st century BCE that the Chinese were making regular observations of sunspots. The first known drawing of sunspots were by an English monk, John of Worcester. I love names in Europe at that time. You know, your name was the place you were born, where you lived. And that was in the 12th century. And here's an example of a page from that manuscript that shows the sunspots. And then the earliest confirmed telescopic observations were actually by an English astronomer named Thomas Harriot in 1610, and Parisian astronomers Johannes and David Fabricius a year later. Galileo did not discover sunspots, as some people have claimed. He didn't start observing sunspots until actually 1612, and he made many detailed drawings of sunspots, and he discovered actually the sun rotates. And from these drawings, his observations, he was able to estimate the sun rotates about once a month. It wasn't until later that the sunspot cycle was discovered, and that was done by an astronomer named Henrik Schwabe in the middle 1800s. Here's an example of his drawings where he numbers them, he basically kept counts, and from that he was able to deduce roughly a 10-year period of sunspots. The first photograph was in 1845 by a pair of French physicists, Louis Fizeau and Louis Foucault, who you might know famous for his pendulum, Foucault pendulum. And here, by the way, is an example there. That is the first photo of the sun. You can actually see, yes, there are some spots on it. And the link between solar activity and geomagnetic activity, in other words, aurora, was not put forward until the early 1900s by a Norwegian astronomer, Birkeland. His ideas actually weren't confirmed until the 1960s, though, when we started sending space probes up to study the environment of space. Now, you might be saying to yourself, wait a minute, Don, I thought you were talking about star spots. Why are you talking about the sun? Well, the sun is a star, right? Okay, so technically I am talking about star spots. But okay, we're interested in other stars in this case, right? So, and of course, we'll take a little trip back in time again, where the idea of spots on other stars began. And we'll start with the discovery of, let me turn off this other set of lights here, it's a little bit more visible. Discovery of Mira in the 16th century. A star in Cestus was noticed to periodically appear and disappear. And again, it was discovered by their father-son team, by the way. Johannes and David Fabricius discovered it. And it wasn't until many years later, well, first of all, let me say, there were some variable stars known before this. In fact, ancient Egyptians probably recorded the variation of a star called Algo as long ago as 3,200 years ago. And there's also the occasional quote-unquote guest star that would be observed by Chinese and other observers before that. Eventually, a period was discovered, and it was figured out by this guy, Ishmael Baruch. I can never pronounce these weird names. In the middle, in the 17th century, and he was actually the first to propose a model for why these stars varied. And again, forgive my crude 3D animation skills, but the model essentially was you had a rotating star, and half its hemisphere is covered by a spot, and as it rotates, the brightness changes over time. And that was, again, to explain why these stars like Mira would appear and disappear. And this basically became the default model. As I found more and more of these stars, it became the default model to explain why these stars would change over time. Now, does anyone know this guy, Arthur P. Norton? The Star Atlas, right. He's the guy who created the Star Atlas that a lot of us often use, of course updated by Will Triton. But he was an astronomer in the middle 1800s, and he even went so far in a paper to summarize the dominant view in the time of what caused stars to vary. And I'll read this here, it's probably small. The most probable explanation for the phenomena of variable stars is they are self-luminous bodies rotating upon axes, like the sun, and having, like him, spots upon their surface, but vastly larger and more permanent. By the rotation, these spots are brought periodically around onto the side towards Earth, and accordingly to their size, occasion, a diminution of the light of the star, or make it entirely to disappear. This model has problems, though. All right, as more observation of these things were made, and however, why doesn't it work? Well, we have an example of a rotating sphere with one dark hemisphere, and that is the moon. As the moon goes around the Earth, it goes through phases. All right, and if you make a light curve of the change of light over time, it has this very distinctive shape. All right. However, let's look at the light curve of a mirror. Doesn't look anything like that, does it? So that was a problem. And what astronomers would try to do is, okay, let's not assume it's a sphere. Let's instead assume it's an ellipsoid, or an ellipsoid rotating on weird axes. None of these models would produce light curves that fit what was being observed. Okay. Jump a little bit ahead here to a guy named Pickering, who basically cataloged variable stars, and he cataloged them according to their light curves. Start with the first type he called temporary stars, which would brighten suddenly and then decline over time and eventually fade out of visibility. Again, the Chinese guest stars. What are called irregular variables. Their light curve doesn't change periodic fashion or by the same amplitudes. They're irregular. This third type were the long period variables that change pretty regularly. The example, again, Mira. The short periods, often also called Cepheid variables, and they're related stars. And the final, of course, are the algol type stars, which by this time they figured out are eclipsing binaries. They're two stars that eclipse each other as they revolve around each other. At the same time, Pickering also proposed models as to why these stars varied. The temporary stars he attributed to stellar collisions. That these two stars would actually collide and create a huge explosion that's brighten and then fade over time. The irregulars he attributed to star spots. The mirror variables he also attributed to star spots, but he wasn't sure because the amplitudes of these stars are so large, the spots would have to be so big. Again, covering half a hemisphere, he just didn't buy that, and again, also because they didn't fit the light curves that well. And the short period variables he attributed to, again, rotating ellipsoid stars with uneven brightness on their surfaces or rotating spotted surfaces. And then, of course, again, the eclipsing binary model for the alpha type stars. Eventually, spots completely fell out of favor as far as an explanation for why stars vary over time. Is mostly by the work of three different astronomers who basically put forward pulsation as an explanation for why certain stars varied over time. That includes the Cepheids and again the mirror variables. The final nail in the coffin for spots was a pair of mathematicians who try to use different spotted surfaces again to model the light curves of these regular variable stars, and they just basically showed through mathematical proofs there's no way you can do it. However, it was at this time that astronomers actually began observing spots. They didn't realize it. And this comes because of a new observational technique called photometry, which is basically using something called a photometer to count essentially the number of photons coming into the telescope And you could more precisely measure the brightnesses of stars down to the 10/100ths of a magnitude. And the first stars that they started actually observing spots in, not realizing it, are, again, eclipsing binaries. In particular, W Ursa Majoris. As you can see, the light curve, isn't quite symmetrical. Right? Something was distorting the light curve. In fact, they found several stars that this occurred in, and they called it light curve distortions. Here's another example of it. All right, you can see how these light curves are completely unsymmetrical. And by the 1950s, there were so many of these that they were observing, it became a pretty hot topic in astronomy, trying to understand what was going on, why these light curves, some of these eclipsing binaries were not symmetrical. And that led to all kinds of speculation about it. A number of mechanisms were proposed. A couple of, was absorption of light by gas streams or hot spots, both caused by transfer of gases from one star to another. The earliest observation of spots on single stars occurred in the 1930s, and here's the star in question, Lambda Andromeda, and if you can look here, it's very unsymmetrical. It's obviously not an eclipsing binary. It's very irregular, all right, but it's not the same amplitude as the irregular variables. The light curve, the shape of the light curves are irregular. So nothing could explain, as far as they could determine, the variation of the star. This was a unique star. They were able, though, to deduce a rough period of around 55 days. And as I said, it was basically unique at the time. They didn't know how to classify this star or what the mechanism was. And it wasn't even added to. There was a general catalog of variable stars, with GC, VS, and this star wasn't even added until the 50s, and it was added in a supplement, and it wasn't even added with a classification. And there it sat for a long time, and no one knew what to do with it exactly. The first, though, to reintroduce the idea of sunspots was a guy named Gerald Cron, who, over the course of observing about a half dozen stars, drew this conclusion. This is from one of his papers. The similarity of those phenomena to the activity on the surface of the sun permits the conclusion that many of the photometric peculiarities may be caused by activity similar or identical to that associated with sunspots. All right. However, his work was overlooked and uncredited when finally the idea of star spots started to get more in the mind of astronomers at the time. The rediscovery is often credited to several people. Hofmeiser, who studied T-Tauri-type stars as the early stars that are just forming, very active. Another astronomer studying a star called BY Draconis. Here's the light curve for it here. And another pair of astronomers, Krominski and Kraft, who were studying stars similar to BY Draconis. And in fact, by 1971, this was designated as a class of variable stars and added to the catalog. By the 70s, early 70s, star spots basically came back into quote-unquote fashion as an explanation for the variation of some stars. Now, what exactly are star spots, right? Well, to begin with, we got to understand, what is a star? So, other than Ness and Brad, who can tell me what a star is? What's a star?
Tom Hanks is a star.
Right.
Nuclear explosion in space.
Basically, it's a big ball of gas that's producing a lot of heat and light through the process of nuclear fusion, of course, right?
That's my guess.
So, what are different types of stars? I'm talking about just regular old stars like we observe in the sky.
Oh, be a fine girl, kiss me.
Right, okay, yeah, that's communication, right?
That's right.
The problem with this is, there are actually only really three types of stars. This is an arbitrary classification, right? It's just based on the color and temperature. And as scientists, we don't like arbitrary designations of things, or arbitrary categories. We like to categorize things based on more fundamental things, okay? So, and the defining thing that really tells you what a star is its mass and, well, of course, the temperature, but how that temperature, how the heat from those nuclear reactions get out of the star. Okay, and that affects the overall structure of the star. All right, and there are three ways you transfer heat. All right, high school physics. What are the three ways you transfer heat? Right, conduction, which is basically when you heat something up, the atoms begin to vibrate, they get more kinetic energy, and they transfer that through the object, right? And then convection, here's an example, of course, Earth is a convecting object. You get the internal heat from its core, convects out, that's what drives plate tectonics. All right, how many were around 1960s and 70s? All right, I'm going to say, if you remember the 60s and 70s, you weren't doing it right. Okay. And then, of course, radiation. Right? For example, how you warm up at a campfire is the radiation coming from the fire, right? Well, it turns out that as far as way stars transfer heat, it's mostly convection and radiation. Conduction plays a very small role in how stars transfer heat. In fact, conduction is the least efficient way to transfer heat. Okay? So only the last two are important. And again, how does that affect the structure and heat transfer in the star? Well, as I mentioned, it mainly depends on the mass of the star and the fusion process in the star. Okay? And these are the three main types of stars and how they transfer heat. All right? For stars that are about less than half the mass of the sun, they are fully convective bodies. So as reactions happen inside the star and it releases all that heat and energy, convection is what drives it out to the outside part of the star. All right? In cases of stars that are larger than a half solar mass, up to about 1.5 times of the mass of the sun, there are two processes, the radiating process in the core and convective processes on the outside part of the star. Okay? For stars larger than about 1/2 times the mass of the sun, it's almost like the star turns inside out. The core is convective, and the outer part is dominated by radiation transfer. Now, we mentioned the fusion process. What exactly is the fusion process? What's the star fusing to make all that heat and light? Hydrogen, right? It's called a PP reaction, proton-proton reaction, right? Here that process. All right, you take 4 protons, and eventually you'll wind up with a helium nucleus and a lot of energy, right? Well, it turns out that this is the dominant process, this is the dominant way that energy is produced in stars much smaller than the sun, right? The sun, this only accounts actually for about 90% of its energy budget. The other process in the sun that produces about 10% of the energy, and most of the energy in larger mass stars, is called the CNO cycle. All right, it's called CNO cycle because these elements act as catalysts that eventually take hydrogen and fuse it into helium. The catalyst is just something that when you react with it, you get it back. All right, and for stars about roughly 1/2 times the mass of the sun larger, this is the dominant energy process. Yeah, proton fusion still happens in those stars, but this produces most of the energy in larger stars. Okay? So, it's the fusion reaction and the mass of the star, and there's only 3 kinds of stars in reality. Okay? Now, as far as spots go, right, the important thing, well, I'm going to lay out the pieces individually of what forms spots. We're going to focus on stars like this. Roughly, we call these sun-like stars. Stars are roughly about the mass of the sun, about and have the same kind of structure and temperature. So let's take a slice of a star, say the sun. All right, this is what kind of the structure of the sun-like star. You got the core here, where all that nuclear reaction is going on. It's very hot, you know, roughly about 15 million degrees. All right, and radiation is what transports the heat through most of the star. Okay, in the case of the sun, that takes up about 70% of the sun by its volume. All right. This part here, there's a really thin layer. We call it the technicline. All right, I'll get more detail on that here in a moment. But that's where it transitions to where convection takes place in the radiating process. But the temperature only drops a few million degrees in that distance. The remaining layer, the remaining third, the heat transfer is so efficient that the temperature goes from a couple million degrees to just about 10,000 degrees on its surface here at the photosphere. All right. Part of the reason for this is just the radiation from the reactions takes a long time to work its way out. All right, because the center part of the sun is very dense. That radiation can't just go straight out of the sun. All right, it kind of just bounces around. It takes about around 100,000 years actually for a given photon to make its way out of the sun. All right. And when it reaches the surface, we call it the photosphere because that's what we call the surface of last scattering. The light is actually free to travel on and make the 9-minute journey, say, between the sun and the earth. Right? So, and at the surface, at the photosphere, you can actually see the convection. Right? This is kind of a little movie looping that shows that convection process. We call this granulation. All right? And to give you an idea of the scale, these cells typically are on the order of the size of Texas. Okay? The other key to this is something we call differential rotation. Of course, the sun rotates, as we mentioned earlier. Galileo observed that. And here's a little movie that shows it rotating a little bit. However, you can't really see in here any differential rotation. All right? It takes a long time of observing observing sunspots and the rates they go across the sun to see the differential rotation. Here's a chart that shows the rate of rotation. Turns out the core pretty much rotates uniformly about once every 27 days. However, at the equator, it rotates a little bit faster, about 25 days. And as you go towards the pole takes a little over a month, about 35 days to rotate around. Why? Well, it has to do with the convection. All right? One of the things that convection is doing is it's carrying away the angular momentum of that spinning core. All right? And as it carries it away near the equator, it can carry it away a lot more efficiently than near the poles. All right? Here's a little chart that shows this in more detail. Again, this is about from half radius of the sun to the surface. And it's right around this point, about 2/3, a little over 2/3 of the way, that the differential rotation starts to show up. And you can see at the different various latitudes the rotation rate. Okay. The other key to this are magnetic fields. Of course, the sun is a big ball of hot plasma, and plasma carries they're charged particles basically, and it creates a magnetic field. The sun, you think the sun is almost like a big bar magnet in some ways. However, when you couple it with with differential rotation, because the sun's not solid and it rotates differentially, those magnetic field lines get drawn around the sun. They wind up and get twisted up with each rotation. Why? Well, it's a process we call flux freezing. And what that is, you take a given packet of plasma in the sun, right? It's embedded in the magnetic field of the sun, but when you move charged particles, you also create a magnetic field, and it makes it a stronger magnetic field that grabs a hold of those lines, and when you try to move a section of that plasma, it tries to drag the magnetic field with it. Okay? And this goes also in explaining, well, we need to talk about why spots are even dark, why they're darker than the rest of the sun. Well, we start with these, what we call flux tubes, that get twisted around the sun as it differentially rotates, and some of them, through a process called magnetic buoyancy, will pop up out of the surface. And it's at the footprint of those magnetic loops that the action happens. Okay? And this leads to cooling, in part because this suppresses some of the convection, trying to get heat out of the sun. All right? Basically pushes the convection aside and it makes the spot cooler. And interestingly, it will also, because of this, because it pushes some of the convection off to the side, make the areas next to the spot hotter. So in fact, when the sun has a lot of spots on it, it's actually brighter than it would be if there were no spots there. You'd think spots would make it darker, but actually it makes it brighter.
What's the temperature variation?
About 1,000 degrees. Okay? And again, because these magnetic fields, one of the reasons it also cools is some of the gas, because it can't move sideways, it can move freely along the magnetic field lines. That decreases the density of the gas in the area and allows it to cool as well. And again, they act like, in a sense, magnets. In fact, I have a little example here you can come up and look at later. I got a magnet with some iron filings. You can clearly see the magnetic field line. So come check that out here later on. Here's a little movie that shows that gas actually flowing along those magnetic field lines between the spots. And here is what's called a magnetogram that shows the strength of the magnetic field on the surface of the sun. These flux tubes actually have very strong magnetic fields. And the scale of them, they're usually about 100 to 200 kilometers or so in size, but they can get up to 4,000 kilometers in size. And they're usually 1 to 2,000 kilogauss, which the Earth's magnetic field is roughly about a gauss or so. So it can get thousands of times more powerful than the magnetic field of the Earth, and there's even been some measured up to 10 kilogauss.
That's a Tesla, isn't it?
What's that?
That's a Tesla, isn't it?
No, it's Gauss.
No, a Tesla isn't, you know, the...
A Tesla is a unit, yeah, but a Tesla is, I can't remember how many Gauss all do. Do you remember how much yeah, I think it's like 10 to the 3 Gauss per Tesla. So,
unit of measurement in an MRI machine, so that's good.
right. The structure of a sunspot is a cool inner part we call the umbra, and this lacy kind of outer part we call the penumbra. This part is the part that's roughly, again, about 1,000 degrees cooler than the photosphere temperature. And another effect of this, because this part of the sun is cooler, when you cool a gas, it also will compress a little bit and become a little bit more dense, and the sun's gravity pulls it down a little bit, and the spots are actually three-dimensional. They look like they're just flat on the surface, but they're actually sunk in a little bit into the surface of the sun. And they tend to go down pretty deep too. In effect, again, the convection is trying to come out of the sun, and here, as you can see, kind of a slice cutaway of the spot. I mean, can go, about 10,000 kilometers or so down into the sun. Put all this together, and again, noting the sunspot cycle, it's actually closer to 11 years, the cycle. It'll be basically figured out. And it's really, here's an image that shows the sun over the course of that 11-year cycle. All right, you can see it starts relatively quiet, and then it gets more active, and then that slowly winds down over the course of the cycle. We're currently coming out of the last solar minimum. I just saw they think the next solar cycle has started, so hopefully we'll start seeing a lot more spots on the sun, particularly when we do daytime programs here at the observatory. Next we have a little simulation that shows that reversal happening. What this is showing, this is the magnetic field of the sun, particularly the layers just under the surface, and as the cycle progresses, you'll see the magnetic field will flip over. The reds you think of as north, and the blue think of as south, and you can see the entire thing, the sun magnetic field will actually flip over each cycle. And the total cycle flipping from north back to north takes about 22 years. Solar observing today has come a long way, both with ground-based and space-based observing. Ground-based, particularly, has really advanced in, here's the Big Bear Solar Observatory, for example, and it gives the really, really high-resolution images of the surface of the sun in multiple wavelengths. This is an observatory in the Canary Islands that produced that image I showed you earlier, the sun, really high-resolution image of the sunspot. And, of course, with everything, there are pros and cons. Pros of ground-based observing, they're cheap. Observatories are cheaper to build and operate. The technology, of course, is vastly improved. The cons are, of course, weather, because you're on the ground, you're affected by the weather. Limited observation windows, i.e. you can only observe the sun when it's up. All right, and you can really only see one side of the sun at any given time. Of course, the sun's a sphere, it's a three-dimensional body, so at any given time, you're only seeing essentially half the sun. Space-based observations have come a long way. This is the Solar Dynamics Observatory, and this is an example of solar observatories that we've launched in the past. And again, we can see a lot more wavelengths, and again, here's that magnetogram I showed earlier. That's from the Solar Dynamics Observatory. But we can also, again, see wavelengths that we can't see here on the ground because of Earth's atmosphere. And of course, they have pros and cons as well. Pros are 24 hours of observation. You don't have to worry about Earth getting in the way. You don't need to worry about weather, of course. No atmosphere up there. And you can see more of the electromagnetic spectrum that's not absorbed by the Earth's atmosphere. And one mission we launched a few years ago called Stereo helped us get a 360-degree view of the sun. For a while, we were able to observe the sun completely, not just from Earth. Cons, well, they're expensive, right? Build them, launch them, and maintaining them, of course, is next to impossible. You can't really, something breaks down, you can't go up and repair it. They're susceptible to solar radiation. Okay? Of course, sun releases a lot of energy in the form of coronal mass ejections and particles that can damage electronics. And you might get hit by micrometeorites and other debris while you're up there. You're not protected by the Earth's atmosphere. As far as observing spots on other stars, how do we do it? All right, well, there's actually several techniques that have been developed over the years. One of the earliest one was called Doppler imaging. And that is basically looking very closely at the spectral lines of the star over time as, for example, spots rotate in and out of view. It actually changes the shape, which is also a measurement of velocity of the spectral lines. All right, and then from that, you're able to deduce the relative size and position of spots on the star. Another technique called speckle imaging is basically taking very rapid pictures where you can see here what the twinkling effect, or what's called scintillation, caused by the Earth's atmosphere. As the star light passes through Earth's atmosphere, the atmosphere, of course, is in motion, distorts the light, And what we're able to do is by taking these very rapid pictures, occasionally you can actually see the star, all right? And you basically just selectively combine those, stack them together, and you can get very high resolution images. The next two kind of combine because they're often used in combination. That's adaptive optics and interferometry. Interferometry is taking the light of two telescopes and combining it together. And active optics is where you're literally changing the shape of the mirror in order to cancel out the distortions caused by Earth's atmosphere. This star is called Pi 1 Grusus. It's a red giant star that they are able to actually image the surface using this technique. And you can see this star exhibits granulation just like the sun does. Final technique, something called light curve inversion. Right, and that's the technique I want to focus on. All right, what is light curve inversion? Well, it was developed by a guy named Walter Wilde, and the technique basically was developed initially to image the surfaces of distant bodies like the outer planets and small bodies like asteroids, dwarf planets, and things of that nature. Here's an example. This is the surface of Pluto, generated by light curve inversion. And we can compare that to this is Hubble Space Telescope image of the surface of Pluto using a slightly different technique where they took advantage of eclipses of the moon Charon as it orbited Pluto, and they were able to generate what's called an albedo surface map from that. And as you can see, okay, that pretty closely matches. And let's compare New Horizons image of Pluto. As you can see, this is a very good technique for imaging surfaces of bodies. All right? Yeah, the reason I shifted it is because for some reason the Hubble image, they started it at the longitude of 270 as opposed to 0. So I wanted to line it up to make it easier to see the correlation. So. And later on, our own Dr. Robert Harmon and a colleague of his developed a modified technique for imaging the surfaces of other stars. And again, that's what I'm going to talk about. What it essentially is, we measure the light curve of the star, right? Its brightness over time, okay? And we note that there's a maximum intensity, all right? And we use that as the basis to also assume the photosphere temperature of the star, okay? And then we take a model surface, divide it into patches. There are equal area patches along the lines of latitude, all right? And then what we do is we make assumptions about, again, the photosphere temperature, the spot temperature, something called limb darkening, and that's based on the effect where the center looks brighter than the edge of a star, like the sun. All right, you may notice sometimes pictures of the sun that looks like it's brighter in the center and a little darker at the edges. That's an effect of the opacity of the gases in the star. And, all right, and also assume the rotation line, what the tilt of the star's rotation is relative to the sky as viewed from Earth. Okay. And here I have, these are simulations that basically show, again, how this technique works. So we assume a spot, all right, and then see how the program that we have creates the model of the stellar surface relative to the position of the spot on the star's surface. You can see it does relatively well when the spot is almost face onto us, as opposed to it has a little bit more difficulty when it's near the edge of the star, rotating in and out of view. And what we do is try to match the light curve of these simulated surfaces to the actual light curve of the star that we observe. We try to get it as close as possible, and that should ideally be the actual location and size of the spot on the star. And we also have to take into account also noise. Noise is an unfortunate side effect of collecting data on different things, and you have to account for it, of course. So we have to make certain assumptions about the noise levels that we are seeing. Summarize my project. What I'm specifically doing, or what we're specifically doing, is looking for differential rotation stars, trying to show that stars, like the sun, of course we know that the sun differentially rotates, but do other stars actually differentially rotate? Instead of assuming it, we want to show that it's actually the process is involved in creating spots on other stars. And I'm looking at two stars. Currently, I'm looking about 20 to 30 years worth of data on both these stars. So it takes a lot of time to churn through this because I'm looking through, it doesn't show it very well, but hundreds and hundreds of light curves basically over the course of decades, and running them through this light curve version process, generating the stellar surfaces and measuring then, again, how do we determine differential rotation? Well, of course, I'm looking for the longitudinal spot drift rate versus latitude. In other words, how fast the spot moves relative to the latitude that it forms on the surface of the star. Here's an example from one of the stars I'm working with. And you can see the spot here. This is the meridian, it'd be like 0 longitude. And this is looking at how this changes over time. Okay? Looking at each light curve and seeing how these spots change over time. And here's an exclusive kind of preliminary early results. What we're looking at here is this is a plot of this is the longitude versus the drift rate. And right now what we're seeing is there's it's hard to see, there's a trend line here basically in the data. There's a lot of scatter, unfortunately, because again, because of the noise of the data. But it has a negative incline, which is indication of sun-like rotation, differential rotation. In other words, the equator rotates faster than the poles do. So an early result, there are some rare instances of stars that are the opposite, where the equator rotates slower than the poles. Those are very rare. Another one of the stars I'm looking at might have that. So it might be something hopefully that'll be publishable, basically. Now you might be asking yourself, okay, what's all the benefits of this? Well, this is where the beauty in the subtitle of my talk comes in. Okay? One of the benefits, of course, is understanding the sun and stars like the sun. And that has applications to things like climate science. Okay? You know, climate change is pretty much one of the big talking points right now in our country, and how we address it and whether or not it even exists. Right? But with this one graph, you can actually see that climate change is happening and it's human induced, right? Because often one of the talking points people who don't believe in climate change they'll talk about the sun, right? The effects of the sun on climate. Yes, of course, the sun affects climate, right? It has throughout history. However, the problem is in recent times, though, it's been decoupled. The climate's been, in a sense, decoupled from the activity of the sun because of us introducing carbon dioxide at an ever-increasing rate. Let's zoom in on that kind of later period, and as you can see here, this is the solar irradiance. In other words, how bright the sun is over time throughout the sunspot cycle. And remember what I said, the sun's actually brighter when there's more sunspots. So this is when there's high sunspot activity, this is when there's low activity. All right. This is global temperatures over time. As you can see, there is a little bit of correlation. It drops in temperature during solar minimum, a little bit increase during solar maximum. However, look at the trend over time. All right. Notice which it doesn't match this. That's the carbon dioxide, though. Right. The trend matches the increase in the carbon dioxide. Right. And notice a little side thing. What do you think these little squiggles are? Periodic squiggles are.
Seasons.
That's right, seasons, right? The change in vegetation, right? So, again, don't think that planting more trees is really going to help much. Unfortunately, it's not. I mean, it's a wonderful thing to do. Of course, we need more trees, need more green. but it's not going to fix the underlying problem, the increasing amount of carbon dioxide in the atmosphere. And the other benefits, there's technological benefits, such as, we rely a lot on communication satellites, satellite technology, and our power grids are actually susceptible to activity of the sun. There was an incident in the 90s where a geomagnetic storm knocked out a significant part of the power grid in Ontario. It induced extra current in the power lines, and it blew out transformers, and it took several months to fix most of the problems. And of course, there are those existential questions, where did the sun come from? How does it work? Things like that. So, I guess I'll wrap that up, and you have any questions, existential or otherwise? Yes?
Don, where are you sourcing the light curves from?
For the data that I'm working with?
Yeah.
The data I'm working with, it comes from the one collaborator, Dr. Henry from Tennessee State. He has automated telescopes they're out in Arizona, and he basically has a program of just regular observations he does of certain stars. And he's basically collected, like I said, these decades worth of observations, and there's too many for him to do alone. So he reached out to Dr. Harmon and myself and to collaborate with him on going through some of this data and to be able to do this project, basically, yeah.
How do you make the stars?
Again, they're from his program, and these are particular stars that haven't been analyzed in great detail. So we're basically the first people to look at this data in detail.
Are they like red giants, or just,
What's that?
are they like red giant stars, or?
No, they are solar type stars. One of them is they're both slightly cooler than the sun. One's a G9 type star, and the other one's a K0 type star. They're both main sequence, and yeah. So the key thing I want you to take away on that regard is there's only a very special class of star that can produce spots. Right? You need surface convection. All right, and it has to be a certain mass range. All right, red giants, supergiant blue stars, red giants cannot produce spots, at least not spots in this regard, because those are magnetic. That's because of the magnetic activity that the spots I'm talking about. You can get hot and cool spots on stars that are highly convective, like red giants and red dwarfs and things like that. And the other interesting thing is, stars larger than the sun, much larger than the sun, they don't even actually have photospheres. Because they're so hot, they're so bright, their surface density is so low that again, because you don't get convection on the surface. So if you could, quote unquote, look at like an O-type star without going blind or anything, the star would actually look fuzzy. All right? It wouldn't have as well defined of a surface as like the sun does. Yes?
What are the models now as far as figuring out the intensity variation of cycles when everything from like the last, weaker cycles to the modern minims or really strong cycles?
That's still a mystery. Yeah, we don't know. For example, there was the modern minimum, where there were virtually no sunspots for decades. There was also a brief period around our time of the Revolutionary War in this country called the Summer Without Winter. Probably is linked to the lack of sunspots.
They have theories though?
I
think that might be where that.
It relates to just below the surface of the sun. Let me go back to that slide here. Speed this up a little bit. It may relate to, in a sense, the way the differential rotation happens in the mid-latitudes here. As you can see, particularly around this latitude, it's pretty much coupled with the rotation of the core. And that might I mean, I'm still not clear on it myself, but it might be here where the cycle gets kicked off. But there might be some mechanism of the way the convection works, and the way there are subsurface streams of gas that might form and actually cross the layers near the boundary here that I mentioned, the tactical line between the various layers in the core that might interfere with that process getting kicked off. That's the easiest way I can explain it. Yes.
Chaotic process. The pictures that you have in the simulated star spot images show spots that are, by solar standards, uncommonly large. I mean,
Well,
yeah. Is that an artifact of the resolution of the technique, or are the spots actually much bigger on other stars?
well, in some cases they are, and some stars they are much, much bigger. There are some stars that exhibit what are called polar spots as well. The stars I'm looking at, though, they're a lot closer to the sun. The spots are, even though looks bigger, in fact, there's a lot of noise. Again, there's a lot of noise, and the software will do is some of the noise you can't, but have some of the noise get represented as part of the spot. So some of this might be noise. The spot actually may only be about 8 big. All right. These spots, unfortunately, are at the limits of the resolution of this technique as well. And that also increases the amount of noise.
So the darkness of that spot relative to the model there is much less contrasting. I mean, it's actually
Right. Yeah.
it's very,
The
very
contrast
low.
is increased
Yeah.
in order to make it a little bit more visible. Yeah. Again, the photosphere of these stars is roughly about 6,000 degrees. Spots we're assuming about 1,000 to 1,500 degrees cooler.
And okay, so the orientation of the star might also have an effect on.
Yeah, we have to
how
assume,
could
because
this-
we can't see, we actually make an assumption. What we're doing now is we're assuming 3 different inclinations, 3 different axial tilts, 30 degrees, 45 degrees, and 60 degrees.
Okay.
And then basically modeling the light curve based on those different orientations and getting a best fit. And that's what each one of these is relative to. Again, there's 30 degrees, 45 degrees, 60 degrees, and hopefully we can narrow down what the actual orientation of the star's rotation.
So if we're looking straight down at the top of the star, this isn't a very good technique.
Right.
If the spots just go around.
It's not going to rotate. Yeah, the star's not going to vary in brightness, and if it's 90 degrees to us, it actually doesn't work very well either.
Because you're not able to differentiate between north and south.
Exactly. Yes.
Because of all the data that you have, and this might be beyond what you're working on, but I don't know if you've heard, if you found like a stellar cycle yet on other stars. We know our sun, 26 years to flip up and down, or not 26 years, whatever it is.
Right.
22 years, 23 years. Have you found these other solar-like stars any data that shows a similar 11-year cycle, or is it different? Like this one's a 23-year cycle, this was a 50-year
Right.
cycle?
Yeah. In fact, this star here, which HD 220182, which is a variable star in Andromeda, has a rotation period of about 7 days, almost 8 days. In other words, it's rotating faster than the sun, and the spots actually persist a lot longer. But over the course of this 30 years worth of data, we are seeing a trend as far as the number of spots, the size, and where the spots are forming and things like that. So, again, it's just another indication of differential rotation.
Right.
But again, we're not going to draw a positive conclusion until I've gone through all the data and we see, where that line's actually.
Right, but you're seeing the variations, you may not
Yeah.
know what the actual variation period is,
Right.
but you're
When
seeing.
this star, I'm looking at maybe 30 years,
Okay.
a 30-year period. This one I'm not sure yet because I've only just begun to go through some of the data on it. But yeah, there are indications in other stars of a solar-like cycle. There have been other stars documented that have similar types of cycles.
And
So-
I just think it's interesting, I just wonder if there's like a relation between, how fast the star is rotating.
And that's what it's looking like. It's
Yeah.
looking like there's a relationship between the shorter the rotation of the star, the longer the spots tend to persist. In fact, Dr. Harmon's done a lot of research on another star called LO Pegasi that it rotates once every 10 hours. And it has a persistent polar spot, but it also has these spots that will form at lower latitudes that will last months, or literally months and years. Yeah.
How many years of data does he have?
He's been doing this for about 10 years or so on that particular star. Again, the data I'm working with from Dr. Henry, he's got like 30 years worth of data.
Wouldn't the technology for the observations have changed significantly?
Well, I mean, we've been using CCD cameras since the 80s, and it's all CCD relative data. Yeah, I mean, one of the problems that we've run into is the sensitivity of the chips have changed a little bit over time, the efficiency of the chips, things like that. The data is also a lot more noisy in the older. So it's been a little bit more difficult than these early light curves. There's a lot more noise. And also the problem, of course, again, doing ground-based observing is you're susceptible to weather, when the stars up in the sky and things like that. So there's gaps in the data. So what I've had to do is actually combine 3 rotations of the star, the light curves from 3 rotations, combine them together to average out to get enough data to generate these light curves. So actually you're looking at 3 rotations, which reflects almost a month. And because these curves are relatively consistent, I mean, again, the spots are lasting at least a month on the star, maybe longer.
What kind of declination are those? A high declination, so you can see them most of the year, or
I'm sorry?
do they hide behind the sun when the sun's
Well, yeah, I mean, you have to worry about solar conjunction, and again, just the season when, So, and you also, we like to observe stars when they're at least greater than 30 degrees altitude, because from 30 degrees down towards the horizon, you're getting more extinction, you're looking through more atmosphere, and that affects your measurements as well. So, there's actually, a small window when you can get good observations of the star, and it has to be when it's 30 degrees above the horizon. So it narrows the window of when you can do observations.
So if it's the differential rotation that's causing the twisting of the magnetic field lines and ultimately sort of allowing the spots to form, how do the polar ones work where you're, more consistent and less difference in
because
rotation?
The other thing about the more rapid rotating stars is they don't differentially rotate as much. Let's go back. Let's see. The picture here. because the star doesn't differentially rotate as much, right, the main magnetic field of the star, you know, is dominated mostly by the radiative zone that created by the core of the star, is more dominant. And that effect of essentially the cooling by the gas streaming along those magnetic field lines dominates at the poles.
Oh, so you would expect to find a spot on each of the poles.
Yeah, most rapid rotators that's been observed, they tend to have more polar spots.
So
Is there
the
a
fast
temperature difference in the, is there a temperature difference in those lines? But.
Not in the magnetic field lines, but in the gas.
No, not between the magnetic, between the equator and the pole.
Yeah, yeah, essentially the poles tend to be cooler than the equator.
By how much?
Roughly, again, about 1,000 degrees.
One last question for me. With the faster rotating stars, they're more late, right? They're kind of squished or?
Not in the case of stars like the sun.
Okay.
Because they're denser and the gravitational field at the surfaces are stronger, they don't bulge that much. Even the LO Pegasi, which rotates once every 10 hours, doesn't bulge that much at its equator.
Right.
The stars that you've heard about that really bulge are, again, those giant stars that are more tenuous in their outer layers. So they're not as dense, the gravitational field at their surfaces, the field is weaker, so that's why they tend to bulge.
Okay. Now it makes sense.
All right, well, tell you what, Don, you can still take a few questions after.
Sure.
Let's thank Don.